Welcome to this session, which consists of papers from the journals who have been selected by the editors. Of course, this session should have happened, so some papers have been held for some time in this process in the editor. So in view of the continuous debate on climate change and extreme weather events, the paper have in common the theme of environmental impacts in the application that they consider to illustrate advanced statistical techniques. So our first, unfortunately, one of the presenters is not able to make, so we have only got 2 papers in this session, and so I've given the presenters a little bit of leeway, including we could, for their presentation and also for the, of course, the questions. We will start by a remote presentation from David Bolin, who is in King Abdullah University of Science and Technology and also in the University of Gothenburg. It's a joint presentation with J. Wallin from Lund University. And this is a Series B paper, and he's going to talk about multivariate type G Matérn stochastic partial differential equations, random field. So it's a big methodological advance. And David, you have joined us, so the floor is yours.
All right. Thank you very much. Can you hear me?
Yes.
I guess so. So thanks a lot for the invitation. I'm very happy to be able to give this talk, even though I would, of course, have preferred to be able to come there in person as well, but hopefully next time. Yes, so this is a work that is joint with Jonas Wallin, and it's about a type of non-Gaussian multivariate random fields based on stochastic PDEs. So the motivation is, as the theme of the session, very much in climate data. So there is a growing interest in flexible multivariate models for multivariate data sets. So you can see an example here where we have bivariate observations of temperature and pressure data. So you have the temperature here on the left, where the mean value has been subtracted, and the temperature on the right. And a common task would be that we would like to do some kind of co-kriging of this observation. So we would like to do spatial interpolation. And a typical way of doing that would be to assume that our bivariate observations, yi, are some noise observations of an underlying latent random field x that is modeling kind of the true variables, pressure and temperature in this case. So then the statistical model would then be to design this random field model. And a common way to do this is to assume that x follows a multivariate normal Gaussian random field. And then this model would then be uniquely specified by its mean value function, which is typically modeled using some covariates, such as perhaps altitude or latitude and longitude. And then we have a covariance function that is specifying the dependencies in the model. So the main task is then to specify this Gaussian field through its covariance function. And a common way of doing this, so a common way for univariate random fields, is to use the so-called Matérn covariance function, or you can see the correlation function here, which has 3 parameters. It has a variance, and it has a correlation range parameter kappa, and a smoothness parameter nu that is changing the differentiability. You can see a few examples of it in the figure here. Now, if we want to make a multivariate version of that can be done. So this was suggested by Gneiting et al. In 2010, where they show that you can, for a multivariate model, you can assume that each cross correlation function, so each, if you look at the covariance between, say, the temperature and the pressure, or the field at dimension I and dimension j, that cross correlation function follows a Matérn covariance function. And this works as long as you make some restrictions on the parameters. So not all choices of the different parameters are actually allowed here. So one possibility is to use what they call the parsimonious Matérn model, where we assume that we have a common correlation range parameter kappa for all dimensions. We have some individual smoothness parameters for each dimension, and then the cross smoothness parameters for the cross correlations are explicitly given in terms of the marginal smoothness parameters. Right, so that is one common choice that we will get back to that a bit later. But now the main point that we're interested in is that in many cases, a Gaussian model might not be enough. So there are many features that cannot be handled by Gaussian or transformations of Gaussian models. So for instance, you might have skewness or heavy tails in the marginal distributions, or you could have asymmetries or jumps in the sample paths of the process. So an open problem has been to create practically useful non-Gaussian multivariate random fields. And this has been, so this was the aim in this paper. So more specifically, we wanted to come up with a class of multivariate random fields that have these Matérn covariance structures in space, but more flexible distributions or more flexible non-Gaussian properties. But at the same time, we wanted them to be somehow easy to estimate using likelihood-based methods. So we want them to be flexible, but also possible to fit in a reasonable amount of time. And the main idea then was that we would use stochastic PDEs. So the idea is based on this old observation by Peter Whittle that where he showed that if you have a Gaussian random field with a Matérn covariance function on RD, it in fact solves this stochastic PDE where the right-hand side here is Gaussian white noise, kappa is this correlation range parameter, and beta is a parameter that is related to the smoothness of the random field. And simply put, the approach is that we will just replace the Gaussian driving noise with some non-Gaussian noise. And this is something that we have investigated before in the univariate case. So the question now was, how can we kind of use this idea to construct multivariate random fields? And a natural idea then would be to sort of, if we have this stochastic PDE as a univariate model, would be in the multivariate setting to consider a system of stochastic PDEs. So this is something that has previously been investigated by Hu and Steinsland, where they looked at using systems of stochastic PDEs of this form to construct multivariate Gaussian random fields. So here you have kind of a matrix of operators where the operators are exactly of this form that we had for the Matérn covariance. So now the problem with this is that, so this is a very flexible class of Gaussian random field models, but they do not actually have Matérn covariance functions in general. They're in fact a bit difficult to work with because they have a lot of parameters, and some of these parameters are actually not identifiable. So as a first step, we wanted to see if we can come up with some kind of subclass of models of this type by requiring that all marginal covariances should be of Matérn type. So this was the first question that we wanted to answer. And it turns out that this works. So if we have a system of SPDs of that form where the right-hand side can be some possibly non-Gaussian noise, as long as the different dimensions are mutually uncorrelated, then we say that this is a multivariate Matérn SPD field if this matrix of operators K has a specific form, namely this form, that it can be written as just real and invertible P by P matrix if we have a p-variate random field, times a diagonal matrix with P of these kind of Matérn type operators. And if we make that restriction, we can actually show that then the marginal covariances, so the covariance function for the ith dimension in this multivariate field is of Matérn type. However, the cross correlation function, so the covariance function between dimension I and j, is not generally of Matérn type, unless we have the special case that the smoothness parameters kappa I and kappa j are the same. And in fact, if that is the case, then this is exactly the parsimonious Matérn model that I mentioned before. Okay, so this is so that's the model that we're interested in. So the question then is that enough now? So if we make this restriction, are the parameters of this model identifiable? And it actually turns out that this is not the case. So in the following sense, that we can show that if we have two different models of this type, where we say that they have the same operators, L1 to LP, but they might have, so they have the same operators, but they have different matrices D, which we call dependence matrices. Then they will actually give the same covariance function if these matrices are related like this. So if you can write D as some orthogonal matrix times D hat, then they will have the same covariance function. So that means that this matrix D is not fully identifiable for Gaussian data, because then as you know, then the model is uniquely specified by its covariance. And even more, we can actually, for any matrix D that you start with, you can always find a triangular matrix, which we call DL, that will give the same covariance function. So this kind of shows us that we need to be a bit careful with, if we want to use a model like this for applications, we might have to make sure that we can actually estimate the parameters, and then we need somehow a good parametrization that we know what the parameters are actually doing in the model. And so what we simply will do is that we will parameterize this dependence matrix D exactly like that. So we have a lower triangular matrix DL times an orthogonal matrix Q. And then we have these operators L that will be of Matérn type. So if we make such a parameterization, then we have parameters tau, kappa, and alpha, which determine the marginal behavior. So the marginal variance, correlation, range, and smoothness of each random field, or each dimension. We have this matrix DL that will control the cross correlations in the model. And then we have this matrix Q and possibly parameters in the driving noise that will control non-Gaussian features. So as a specific example, we can look at if we just have a bivariate model, so P is equal to 2, then we can use this parameterization of this 2x2 matrix D. So it is written then as an orthogonal matrix, which is nothing else than a rotation matrix in 2D, times a lower triangular matrix. So we have now two parameters, theta and rho, where rho will determine the cross correlation between the two dimensions, and theta, so this parameter here, will not affect the covariance at all. So for Gaussian models, you can just pick that to any value, and it will give you the same model. So I will get back to what that parameter is actually doing for non-Gaussian models a bit later. But now, so here you can see an example then of the covariance, so the multivariate covariance function for this model if rho is equal to 0.5. So here we have the marginal covariances in blue and yellow, so which are two covariances of Matérn type, and then the red one is the cross covariance function between x1 and x2. Okay, so that is kind of, then now we know how to parameterize these models. So the next question is then, how should we make them non-Gaussian? And in the paper, we present 4 different ways of doing this. So 4 increasingly flexible construction that all are based on using some kind of normal variance mixtures. So we will look at mixture distribution of this form. So if you take a random variable that is, so said here is just the standard Gaussian random variable. V is a non-negative, infinitely divisible random variable, and mu and gamma are just 2 parameters that will control kind of the location and the skewness in the distribution. So these are the type of normal variance mixtures that we want to use. And the simplest way would just be to take our Gaussian driving noise for the Gaussian model and then just scale it with one single stochastic variance parameter V, like this. So this is what we call the type G1 models. We could do the same thing, but we scale each dimension in the driving noise by a separate parameter, variance parameter V. So these are 2 choices that will actually give quite flexible marginal distributions. And there are actually, so many papers in the literature are actually special cases of this. So you can find like student T random field, for instance, or Pareto processes can be written like that. So they would have a specific marginal distribution for the random field. But the problem with them is that these are non-ergodic, so you cannot, from a single realization, estimate the distribution of this random variable V. And they also, if you just look at this random field for a single realization, it just looks like a Gaussian random field that has a variance and a mean that is scaled by this value V. So for applications in spatial statistics where we might be interested in smoothing, then I would say that these are not of so much use unless you are kind of working with replicated data and don't really care about how the sample path realizations look like. So to get more flexibility, then what we propose as the last 2 types of models is to, instead of this Gaussian noise, use noise that is derived from a so-called type G Levy process. So a type G Levy process is simply a Levy process where the increments are of this normal variance mixture type. And you can also make that formal in more than one dimension. And informally, you can then think of what type G noise is. So kind of take the derivative of this process. You get type G noise, which you can kind of think of as Gaussian noise scaled by some kind of variance process. And this will then give us the kind of non-Gaussian behavior. So that's the idea. And then we can, again, have 2 different ways of doing this. We can kind of take just one of these variance processes and scale all dimensions with the same variance process. That's what we call the type G3 processes. Or we can do the full flexibility and just have an independent type G noise for each dimension, which we then call type G4, which is the most flexible model that we are kind of think is the most interesting that we have. We will look a bit more into how that behaves. So here's just an example of a simulation of this model where we take a particular choice of the driving noise. So we take these variances to be inverse Gaussian distributed. So then we will get normal inverse Gaussian or NIG noise. And here you can see then a realization of this bivariate process where you can see that we have, so rho here was 0.5. So we have a positive correlation between the 2 dimensions. And you can kind of see that this very much looks non-Gaussian because of these kind of sharp extremes that you wouldn't really see in a Gaussian process. And we can also look at now, when we have a non-Gaussian model, what happens if you now change that parameter theta. So this parameter theta that is equal to 0 in this example. And that will in fact change the bivariate marginal distributions of this process. So if you look at the field at the fixed spatial location, then you have a bivariate distribution. And the shape of that distribution will be determined by that parameter theta. So here you can see 6 examples of those bivariate marginals you can get without changing the correlation structure of the random field. So this gives us kind of, if you allow that parameter to be estimated from data, it gives us additional flexibility. Okay, so that was a brief introduction to these type of models. So the question then is, how can we work with these in practical applications? And what we will do is then, first of all, we need to discretize these SPDs somehow. And for this, we will use finite element methods. So this was introduced as a method by Lindgren et al. In this 2011 Series B paper, where they proposed to use finite element approximations to get computationally efficient Gaussian Markov random field approximations of Gaussian Matérn fields, exactly by doing a finite element approximation of this SPD representation. And it turns out that the same approach actually works in the non-Gaussian and in the multivariate case. And what we get in the end is that the discretization, that we can call bold script U, it is a Gaussian Markov random field conditionally on a vector V of independent stochastic variance variables, which come kind of from this variance process that I mentioned in the construction. So this kind of conditional Gaussian behavior, it greatly simplifies using this model. So for instance, it allows us to do maximum likelihood based inference. So if we go back to the model that I started with, if we assume that we have some noisy observations of a field like this, then it turns out that we cannot get a closed form expression for the likelihood of this data, but we can actually get an expression for the gradient of the likelihood. In terms of, if we use Fisher's identity, we get this as an expected value over the posterior distribution of these stochastic variances. And that expectation we can approximate using Monte Carlo integration, just by sampling from the posterior distribution of these variance components, V. And this is in fact very computationally efficient, exactly because of this GMRF representation. So we can do that using Gibbs sampling, where we iterate between sampling the V's and sampling the stochastic weights, and each of those steps are very computationally efficient due to this kind of sparsity properties that we get from the finite elements. So briefly, so that means that we can actually use this to approximate the gradient, which means that we can use stochastic gradient descent to estimate parameters in a maximum likelihood way. All right. So finally, just briefly then to see how this actually works. So let's go back to this picture that I started with. So the data. So this was 157 observations of pressure and temperature, and we fitted to this data 4 different models where we either assume just independent Gaussian Matérn fields, a Gaussian field with this parsimonious Matérn covariance function, and then 2 of these Matérn SPD fields, where the first one is Gaussian and the second one uses this Nig noise. And then we evaluated the performance of these 4 models using just leave one out cross validation, where we try to predict the left out value. And here I'm showing then median absolute errors and median continuous rank probability scores. So these are both measures of the accuracy of the predictions, where a lower value is better. And you can see that for both pressure and temperature, this Nig SPD model is actually quite by a big margin outperforming the other models. And it should also be noted here that it took me about 150 seconds to fit this model on my laptop. So it's not really, it's not so computationally expensive to do this. All right, so that was it. So in conclusion, there are surprisingly few flexible non-Gaussian models out there in the literature which are easy to fit for kind of spatial data. And we have presented then one such alternative. And it should be noted that because of these finite element GMRF representations, these methods actually scale as well as their Gaussian counterparts with the size of the data sets. So we can actually use these models for quite big data sets, much bigger than what I had in the application. And we can also, so we have an R package that can be used to fit these models. That's called NGME. So again, the reference here for this talk, the main reference is this, the first paper. The second paper I haven't mentioned at all, but that is the paper that introduces this NGME package. And so if you want to know more about that package, you can look at this paper that was published in Series C also last year. Okay, so that was it. So just as a kind of final commercial, just so as was mentioned in the beginning, I work at KAUST. I'm leading a research group here called Stochastic Processes and Applied Statistics. And I'm looking for both postdocs and PhD students for my group. So if someone is interested, please take a look at my homepage or the homepage for my group. Okay, that was it. Thank you.
Thank you very much, David, for this extremely clear presentation of highly technical material, which you made it sound really, easy, even though we realize there's quite a lot of details behind the floor. I'm opening the floor for questions now or comments. I'm looking also on the online, but so far I haven't seen. Please state your name if you would like to raise a question. Hello. And take your mask off, yes.
Do I need a microphone, Sylvia, or am I audible?
I think you're audible. If you want to come up here, that's fine. I think this microphone works, yes.
Good morning. Thank you, David. This is John T. Ruja. It's a pleasure to see you, not
hello.
to meet you in person. And I should also thank you for the help you've given at least 2 of my postdocs. So thank you for that. I have a more general question. I fully recognize the need for us to construct stochastic processes which are, genuinely non-Gaussian, not just, Gaussian after transformation, although that's often very convenient in practice, but genuinely non-Gaussian. I think that's really important. One of the things that we know about the Gaussian process with the Matérn correlation structure is that it degrades gracefully under compactification of the correlation structure. You can start zeroing off the very small correlations, and the behavior of the process on conditioning tends to be preserved, which is, of course, something that you'd really want to have in practice, because we don't really believe the tales of the Matérn correlation, and it's really convenient to use it in the knowledge that whatever happens in the tails, you're going to get pretty much the same behavior throughout. And that's demonstrated by graceful degradation under compactification, if you like. Now, I think my question is, when we get into these more complex non-Gaussian processes, do we have any reassurance that if we start knocking off the small correlations in the variance matrix, replacing them with zeros, that they degrade gracefully in the same way as they would in the Gaussian case with the Matérn correlation?
Oh, that's a good question. I'm not sure really. So one thing that you will get, of course, is that if you start, so you couldn't construct such a model directly as a solution to an SPD, but you could think of having this kind of non-Gaussian noise, and then you do some kind of convolution model. So you convolve with a kernel that has compact support.
That's
and you
right.
See how what you get then compares to if you would use the non-compact version. So one thing that you directly would get, I think, is that the distribution that you get in the end will be different. So you will not get the same marginal distribution. But how different it is, I guess that this will really depend on what type of non-Gaussian noise you have. So yeah, it's an interesting question, and I don't have any concrete answer to that. So I think it really depends on what type of noise we're using. My guess is that as long as the noise is kind of nice enough, like this NIG noise, you would have something similar, I would think.
I think that would be my guess too, especially for interpolation within the convex hull of the sites. I think there, when you're looking at the conditional behavior, conditional upon the observations, I think you'll be fine. I think my concern would be about extrapolation. I think probably you could get quite rapid deviations from, if you like, standard behavior on compactification after, if you extrapolate. Thank you.
Thank you, Jonty. Let me just check while I'm checking the online chat. Is there any other question from the floor? Can I just ask you, David, a naive question about the flexibility you have for getting the covariance between the cross covariance change over the space, or change over the field, basically. So, you know, because it seemed to be in the example, for example, you were showing with your two images, seemed to be, it was the same sort of cross effect for the whole of your field.
Yes.
Do you have flexibility of having, you know, additional, that this cross structure does changes with the field or not?
Yes, so that's a very good point that I actually didn't mention at all. So as for the Gaussian models, we can make this non-stationary. So we can let the parameters, this kappa and I also had this parameter rho that is was kind of changing the correlation, and that can actually be spatially varying. So this is not something that we didn't use that in this paper, but actually one of my former PhD students used exactly a model like that to model kind of significant wave height data in a multivariate setting. And there that it was really crucial to allow, as you said, for that correlation structure to be allowed to vary over the sea in that sense, in that application. So yes, it is possible. And
of course, you need some constraint. You know, you can't have everything changing all the time. But yes, yeah.
No. I mean, of course, you would then say that it is kind of slowly varying or something like that. If you want to get something that you can actually estimate.
Yeah.
Sylvia, could I come back on that point?
John T. Yes, please. I think there's a follow-up, David, coming up.
Thank you. That's a really good point, and I just wanted to say that exactly as you said, David, Andrew Zamet-Manjan and I have got a two-level process where basically the parameters of the Gauss-Markov random field are themselves a Gauss-Markov random field on a mesh with a much longer edge length, basically, to control the slow variation.
I like those.
Yeah, it's insanely complex, done at global scale, but it can actually be done.
But I think it's in practice it makes a lot of sense for when you think about the applications. Yeah.
That's right. And of course you can Gibbs sample it, and that's the key thing.
Right.
Right.
Any other comments? Well, thank you very much, David, for this presentation. And we are now going to move to our second speaker, who is now going to present in person. So this is Paul Sharkey from BBC Salford, who is working with Jonathan Tawn, Lancaster University, and Simon Brand from the Met Office in Exeter. And this is a Series C paper, talk entitled Modeling the Spatial Extent and Severity of Extreme European Windstorms. So we're all very keen to hear your take on the windstorm. You have the floor, Paul.
And thank you to the organisers for the invitation. So, following on from the theme of environmental impacts, so today I'm going to present some work that I did during the tail end of my PhD, where we developed a stochastic model for windstorms in Europe. And this was a joint project with the Met Office and EDF Energy, and was supervised by John Tawn. So first of all, I'm just going to give you a bit of an introduction to what a windstorm actually is, how they develop, and how they're sort of linked to some other processes that you might have heard of. So windstorms are also, they're commonly referred to as extratropical cyclones. And I just wanted to put in a slide to distinguish between extratropical storms and tropical storms, because tropical storms get a lot of press at this time of year, especially sort of related to systems that you see over the east coast of the US. So tropical storms tend to originate in the tropics, and they derive their energy from the warmth of the oceans. And they tend to move in a direction, and they're not only sort of linked to extreme weather in the US, but those US-based systems, generally you tend to find them along the US sort of east coast. And they generally develop in such a way that the extreme winds and rain that you observe are sort of concentrated in this sort of spiral structure that's sort of centered on the low pressure point. Extratropical cyclones, in contrast, they develop when sort of hot and cold air masses converge in the mid-latitudes. And the points at which you observe the extreme winds and rain tend to be concentrated on at the regions where this convergence happens. So these are also referred to, commonly known as sort of cold and warm frontal regions. So despite the differences in the physics between these two systems, they have some commonality in how they're sort of represented as sort of statistical objects. They're both described, the path which they take is both described as a track that's sort of marked by a sort of an observation of low pressure or vorticity. And you can also describe a distribution of extreme winds, in this case, relative to that point on that track. So extratropical cyclones are largely the most relevant system to us in this part of the world. They generally are observed sort of on a yearly cycle, and they're basically the winter storms that we see every year that are given names by the Met Office and Matérn. And they're generally linked to flooding, landslides, and quite a substantial infrastructural damage, and in some cases even loss of life. Some more extreme examples in recent years was Storm Desmond and Storm Frank. And in fact, the biggest source of spatially aggregated insured losses in this part of the world. And it's from the insurance industry where this sort of problem is motivated. So in order to sort of set premiums and all that sort of thing, insurers use catastrophe models to combine an estimate of the hazard, in this case extreme wind, with an estimate of exposure, so how exposed the property is to these elements. And they use these to combine these factors into an estimate of risk through some loss that's typically quantified as expected financial damage, for example. But insurers are limited by the data that's available to them, and usually we only have sort of historical data related to these systems. So it really motivates a need to look at these systems at some longer time horizon for them to be able to estimate the losses that you might expect with a 100-year storm, for example. And then the two factors that feed into the distribution of losses is both how severe the event actually is, so what do the extremities of wind look like, but also how sort of spatially distributed the system is as well. So we have some challenges before we even get to looking at some sort of stochastic model. So storm tracks aren't freely available from reanalysis data sets or climate model data sets. It takes a lot of work to be able to actually identify these systems from data that we can commonly access in the first place. And there's been quite a lot of work, particularly at the University of Reading, that's gone into sort of algorithmic identification of these systems. And that's typically done through some sort of matching of pressure lows across space-time. On the other hand, if we want to do an assessment of these systems over future climate, for example, we need to be able to run climate models. And if we want to look at potentially sort of more localized distributions of assets, we need to be able potentially to downscale these coarse resolution climate data sets, which is a challenge in itself. But we're still limited by the amount of data that we have here, because even running climate models are expensive, and we're still fundamentally unsure about what a 100-year storm looks like in this case. So this motivates what we're trying to do here. We're attempting to come up with a framework that will allow us to simulate synthetic windstorms. And where possible, we try to preserve the meteorology of these systems where possible. The model that we develop is climate stationary, and by that I mean we don't try to link the characteristics of the storm to any sort of large-scale climate predictors that we can then use to simulate sort of future windstorm events based on climate models. But what we assume is that the outputs of the model that we develop sort of match the climate corresponding to the input data that's used to train the model. So the model that we develop sort of consists of two parts. One is the model for the track and its associated intensity, and the other one is for the distribution of extreme winds relative to the track. And it's the second component of this that is going to be the focus for today. So we're going to do an analysis, not on any sort of future climate projection, but we're going to restrict this to sort of reanalysis data. So we have storm track locations at 3-hourly intervals, and we have an associated sort of intensity measure, which is in this case the relative vorticity. And we use the outputs of the track detection algorithm that was developed by Hoskins and Hodges at the University of Reading. And again, it's a chain of relative vorticity maxima over some spatial field. The associated winds that we use to relate the extreme weather to the storm track, they're taken from the Euro 4 numerical weather prediction model, and that's a downscaling of the ERA interim reanalysis, which is pretty ubiquitous in studies like this, but has since moved on to a new ERA 5 release. This is one slide to demonstrate how we, an example of how we simulate the track associated with a storm. So this is a separate piece of work that was submitted for publication, and I'll provide the links at the end of the talk. But what this does is essentially provide a means of simulating the track of vorticity maxima that takes into account the speed, direction, and the intensity associated with that track. But this isn't going to be the focus for today. So what we're interested in is actually the distribution of wind speeds relative to the track itself. And if we were doing a typical analysis of extreme wind, we would typically take a set of sites. We might fit some sort of model to the sites, and potentially only including observations at which there's a nearby storm. And we might induce some sort of dependence between these sites, maybe through some sort of copula. This is sort of what could be, this is analogous to sort of an Eulerian way of thinking, if you think back to sort of fluid mechanics 101. But what we felt was that it would be, since we're interested in the evolution of the process itself, it would be better to do a more Lagrangian way of thinking. So to actually follow the storm as it moves along the track, and then actually model the distribution of extreme winds relative to that track. So we did a bit of filtering on the reanalysis data to be able to achieve this. So we essentially extracted, depending on where we've observed the storm tracks and the associated pressure lows, we've extracted essentially the extreme winds in some box around the storm center. In this case, I think it was a 1600 by 1600 kilometer grid box. And we felt that that was large enough to be able to include the extreme winds that you'd associate with a system like this. So this example here is the representation of the Burns Day storm of 1987. I think it's referred to as the Great Storm of 1987, or Storm Dario is also commonly known, which had quite a significant effect on the south of England, and did lead to tremendous loss of life in that region. But as you can see here, this is quite a complicated data set. And we really need to be able to actually identify what features we're interested in modeling here and what we're not particularly interested in modeling here. So what we do first is we specify a marginal model for each of the grid cells on the Euro 4 data set. So to do this, we essentially choose a sufficiently high threshold. Below that threshold, we use the empirical distribution function. And above that threshold, we use the conditional model, the generalized Pareto distribution as a conditional model for excesses above that threshold. And there's asymptotic motivation for this that's sort of linked to sort of extreme value analysis. It's a pretty common approach for modeling extremes. And what we do then is we use this marginal model to standardize to common exponential margins. And we focus on the resulting sort of standardized space-time field. So just to give you an example of the effect of this, so on the left is a snapshot of the Great Storm that I mentioned earlier on. And on the right is the corresponding snapshot transformed onto exponential margins. And what we see is that we've essentially transformed from a sort of an absolute observational space to a sort of more relative storm space, if you like. And we've removed the land-sea contrast completely from the data. So we now have a much more sort of smooth structure to work with, which is quite convenient. And what we're ultimately interested in is this cluster of extreme winds sort of south of the storm center that's spatially smooth. What we're not so interested in is these sort of more localized extreme winds that you see in that white box on the left-hand side. Mostly because, well, for convenience, mostly because they won't contribute that much to the distribution of losses. So we feel we can exclude them without causing significant biases to the analysis. So what I'm going to do next is to borrow some of John T's wisdom from yesterday and do some feature extraction. So instead of doing some thinning in time in this case, we mostly essentially throw away quite a lot of our data over space to be able to identify the actual objects that we're interested in modeling here. So I won't go into the technical details of this, but essentially what we do to remove the more localized extreme winds, we do some space-time filtering to be able to isolate the sort of large cluster of extreme winds. Then we only keep the resulting field above some high threshold. And then if there are multiple resulting fields above that high threshold, we then use a clustering approach and then identify the largest cluster, essentially. And that's what we get in the left-hand plot here. This is the shape we're left with. And we see that we have identified the feature of the windstorm that we're interested in, but it's still quite an irregular shape, and it's quite difficult still to model. So what we do for purely mathematical convenience is to enclose this shape within an ellipse. And we can do this using quite a neat algorithm that I only discovered during this particular piece of work, which is called Katian's algorithm, which essentially finds the ellipse of minimum area that encloses these points. And we can exploit the the geometry of the ellipse and the parameters that are associated with that to better define a modeling framework that we can work with. So this object here on the right is what we refer to from here on as the windstorm footprint. It consists of both the shape of the ellipse and also the distribution of wind speeds within that ellipse. So this is what we get here. These are the parameters of the ellipse that we're sort of ultimately interested in. Because again, we're interested in modeling the spatial extent of these fields, but we're also interested in modeling the severity as well. So the key parameters to sort of watch out for here are the semi-major and semi-minor axes of the ellipse, that's A of t and B of t. We also have the ellipse's position relative to the storm center as well, which is quite important actually, because that ultimately links to where the cold and warm fronts are and will sort of determine where the most extreme winds will probably be located relative to the storm track. So we also have the distance between the ellipse and the storm center, and we also have that sort of angle as well with respect to some fixed angle. And we have a couple of other parameters in here as well. We also have the maximum wind speed as well that we observed during the ellipse, which we use for now as a placeholder for storm severity, but I'll come back to that in a bit. So this is quite a complex dependence structure. Some of the observations that we observe from exploratory analysis are relatively intuitive. So as the spatial extent of the ellipse increases, then the maximum wind speed also increase. So like the bigger the storm is in space, the bigger it tends to be in severity as well, and that sort of thing. So what we do is we use some conditional independence assumptions where appropriate, and we eventually translate this into some sort of Markov model, the details of which are in the paper, for transitioning the footprint in time. And when we come to simulate these, we essentially do this using some conditional kernel density estimation. So that mostly encodes the shape, the spatial extent aspect, but we haven't really discussed the actual distribution of wind speeds within the ellipse. So if we go back to the field on exponential margins, under some transformations, we can then assume that this field is a Gaussian process. Ideally, it should be spatiotemporal in nature, but sort of for practical reasons, we just took it we assume just a sort of a fixed time Gaussian process. And we use a Matérn correlation function, but we do allow the scale parameter to vary in time as well. The transformation sort of distribution function that we use, so the distribution of extreme winds, the marginal distribution of extreme winds, I should say, so that's D of t, that depends on track and footprint characteristics as well, so we try to build that into the model. And we also try to incorporate physical constraints where possible as well. It's reasonable to assume that the less extreme winds will be on the perimeter of the ellipse, but we're also concerned with what we call the eye of the storm as well, and that's what I refer to as the storm center. So at the storm center, the pressure gradient is 0, and that typically corresponds to 0, or in practice, very small wind speeds. So we try to build this into the conditioning when we simulate this Gaussian process. So this is just an example. You've seen the first two plots here before. This is what we've extracted from the data. And just to give an example of what that surface looks like when simulating, we've kept all aspects of the spatial extent of the footprint fixed, but we've then simulated the Gaussian process on the right with the physical constraints that I just mentioned. And while there's still some sort of anisotropy that hasn't been incorporated here, even though we have baked in some anisotropy into this process, but it does a reasonable job of replicating what we've seen in the data. So just to put this all together, and again, this gets quite technical in places, so I haven't included the finer details, which can be seen in the paper. So first, we simulate a storm track from the track model. Based on the property of the track, we can then activate the windstorm footprint, and we usually try this on at the time of greatest intensity on the track. Then we can simulate footprint shapes forwards and backwards in time using the Markov model that we've developed. And then we can simulate extreme winds from the Gaussian process with physical constraints. And we continue this until some termination criterion is met, and the details of that I haven't included, but it's generally stochastic in nature and related to how the storm is actually propagating in space and time. So I've included some results here. So what we would typically do then is we would just run this for sort of 1,000 years worth of storms, for example. I think that's what we did in the end. So just to show you some summary statistics that I thought you might be interested in. So here we've done what's known as a composite analysis, where we've essentially taken all the footprints that we've modeled, and we've just sort of superimposed them and formed like a distribution of winds relative in that sort of footprint space relative to the storm center. So we can see that the eye of the storm is pretty visible here. The area around the storm center generally isn't affected by extreme winds at all. And we can see that the 95%, the higher quantiles, the extreme winds tend to be seen in sort of the southwest near the storm center, which is where you would typically see the location of cold fronts. So that's quite promising. And these are all simulated statistics, and they generally match the observed statistics quite well. And so if we were to hand this model over to the insurance industry, which I believe is what we did in the end, but we can also answer questions that are more sort of related to sort of other sort of research-based questions, particularly in sort of extreme value analysis. So from the Monte Carlo sample of synthetic storms, we can estimate the conditional probability of one site being extreme, given that the other site is extreme. And we've done this for a field over northern England. So we've used Lancaster as the conditioning site, and we've used two quantiles, one at the 90% quantile and the 99.9% quantile. And the key takeaway here is that the distribution, the spatial dependence, becomes more localized as the magnitude increases. And this is what we refer to in extreme value theory as sort of asymptotic independence, which is quite interesting. And we can see that doing the same over Germany, using Berlin as the conditioning site, we can see this pattern as well, that we get this sort of more localized features as the magnitude increases. And that's really it. So I just want to do a bit of a shameless plug. So I work for a company called CEvest. We are a startup that is providing climate intelligence to businesses and organizations so they can make decisions that they can adapt to sort of risk associated with the future climate from all sorts of hazards. So we're actively recruiting for statistical scientists at the minute. So we're generally looking for people with backgrounds in statistics and data science, and we're also specifically looking for experts at the minute in spatiotemporal statistics and Gaussian process modeling. So if this interests you, please do get in touch. So those are the two references that are relevant to this talk, and thank you very much for listening.
Thank you very much, Paul, for this beautifully illustrated talk, and I think we've all enjoyed and understand the importance of doing this type of work in the current climate. Are there any questions? Can you please wave? Yes, Tronti.
I don't want to be the only person asking questions.
It's fine. It's absolutely fine. I think that you could just stay in here because I think Paul can hear you from here. Yeah.
Thanks, Paul. This is a really important and challenging problem. So I'm happy to see that you're cranking up the stats machinery. I think it's really paying off. A couple of things. This trick of going to exponential margins is very cute. And you can just see that visually, can't you, by how much it simplifies the structure of the problem. And yet it's almost not lossy at all, is it, really, in that you can almost invert back again. The only thing that concerns me is about whether you get a kink at the point where you join the empirical distribution of the point to the generalized Pareto extension. Do you impose any continuity conditions at that changeover point to remove it?
No, we don't actually. It's generally not needed, I think, when you have the amount of data that we do work at. That smoothness is generally becomes a sort of an artifact of the data. So we haven't needed any smoothing in particular. No, it seems to be okay. Yeah.
I mean, the obvious thing would be a continuity condition on the first derivative, wouldn't it?
Yeah.
It would be easy to put in. It just, you wonder, don't you, because your interest is in extremes, and you wouldn't want a kink, near the point of interest for your analysis. So I think that might be a safe option. The other thing that strikes me about the anisotropy inside your ellipses, I mean, I love ellipses, so I think what you've done is really fascinating. It occurs to me that the simplest solution to baking in more physical anisotropy might be to use a warping approach on your Gaussian process. I know that it's been around for a while and not used very much, the idea of warping, but I think there's been some recent work on it, which suggests that you might be able to exploit that.
Yeah, so I think I didn't go into the detail of this, but I think that there is a warping element in there, but I don't think it's come off quite as nicely as we would have liked. So we've essentially used the sort of ratio between the semi-major and the semi-minor axis as a way of doing that warping, essentially, and that's encoded with using an anisotropy parameter. But I think if we were to extend this work, I think that would need looking at, I think, because what we saw simulated isn't necessarily as physical as we would like it to be, despite it looking like a relatively reasonable realization. Yeah.
Great, thank you.
Thank you, Jonty. Are there other comments or questions? Maybe I could ask you, I think you opened the floor for the type of question, when you were saying the summary, you were showing the summary statistics, and obviously these are the summary statistics that will be used, and you were saying that they kind of match quite well observed summary statistics. I was just wondering if you are thinking about the calibration of this model and ABC type method or whatever for actually, how are you thinking about calibration and
yeah, that's a really good question, and it's probably something we really need to look at when we're looking at sort of estimates of the future climate as well. But essentially, what we're limited to in this sense is just looking at sort of like typical statistical diagnostics. Like we have QQ plots, and sort of it's the diagnostics that we are limited to right now are mostly visual in nature. So we haven't at this stage done any calibration to.
Because basically, how many, so that people get a flavor, how many parameters do you have to choose to run your model, roughly, to start?
So most of the model is sort of non-parametric in nature. So we do sort of depend on sort of setting sort of kernel density, wavelength, bandwidth, and that sort of thing. So it is quite a complex model, and there's definitely a lot of uncertainty in there that we haven't really quantified correctly in this particular study. So I definitely think that some sort of sensitivity analysis is definitely required, and that's before you even get started on the uncertainties in the underlying data sets as well as the storm tracks that have been identified.
So I think there's plenty of methodological issues to pursue in that direction, yes. So you need a bigger team in. Any comments? Can I see? It's very hard to see. Yes, please. Thank you, Judith. It's just with this blinding light, it's nearly impossible to distinguish people in the audience.
Yeah.
Do you have a microphone?
Yeah, sorry. Yeah, just a quick question. Is it best fit is the best predictor?
Can you state your name as well?
Sure. So the name, yeah, I'm Ayub Saeed from Public Health England. I mean, is it best fit the data? Is it going to be best prediction?
So this model isn't necessarily designed for sort of real-time prediction or anything like that. It's basically trying to give us a sort of a more complete picture of risks sort of beyond the data that we've observed. So yeah, by all means, we can only really calibrate to what we've observed in the data. We can't do any sort of validation at return periods that we've not observed yet. But yeah, I think that sort of goes beyond the scope of what we've done here.
Thank you. I think I don't see any question on the online chat, so I think we're going to bring this session to a close. Thank you very much to both presenter and people asking questions. We could start with tea. We could have tea for 5 minutes earlier. Thank you for coming to the session.